All right, I'm starting the recording now. So hey everyone, this is the DS3 Preparing for the Coding Interview workshop. I'm Anurag and this is Laura. And this will be posted on the event Facebook later, along with the slides. I'm gonna go ahead and get started. So my name is Anurag. I'm a current junior at UCSD in the data science program. And over the summer, I was able to get the chance to be an AWS software development engineer intern. And this is Laura.
Hi, I'm Laura. I'm also a junior and I'm currently an intern at QI.
And we're going to talk to you about the coding interview. It's basically a 30-minute process that's highly dependent on your knowledge of algorithms and data structures. And while you might know a lot of these data structures, whether you're like a freshman or a junior, they're used in ways in coding interviews that are probably quite different from the ways you use them in classes. And we want to give you a quick primer on how to use them effectively to deal with a wide range of coding problems. And we'll give you some examples of problems as well as we go along. Moving on. The next thing we should talk about, I guess, for coding interviews is how your problems are judged. The quality of your solution isn't solely based on whether or not you solve the given problem. It's also based on how effective your problem, your solution is in terms of storage and time complexity. So for example, does your solution solve the problem with minimum memory usage? This is considered storage complexity. And does your solution solve the problem with minimal operations? This is considered time complexity. And with that in mind, we'll dive into each of the data structures that are most common in these coding interviews and how you would use them and associated storage and time complexities.
Okay, so here are the simple data structures we'll be covering today. The first one we'll be going over is an array. So an array is a convenient data structure because any element in the array can be accessed by using an index. The time complexity to search for a random element is linear, which makes it a very useful data structure for small amounts of data. However, it gets inconvenient when you are storing larger amounts of data. Moving on to the LeetCode problem. Overall, over here, we are trying to remove duplicates from a sorted array. So because the array is sorted, it's much more convenient. However, we are required to remove the elements in place and return the new length. To target this problem, one method is to start from the end of the list and iterate backwards. So as we iterate backwards, if we see a duplicate element, we only need to reassign the elements we have previously visited one index lower when we find a duplicate element. And yeah. So this next data structure we have is a matrix. It's very similar to a 2D array and very useful for storing multidimensional data. The time complexity to search through this is big O of n, and in this case, n is the size of the matrix. If n was like one dimension of the matrix, and if it was a square matrix, the search space would be n squared. Moving on to linked lists, this is a data structure that is similar to an array, except that it's more flexible. So it can be updated to hold more elements than it was initialized to. Because of this, we can perform operations like inserting a node and deleting a node, which both take constant time. However, we can't access linked list elements randomly by indexing, so the time complexity to search for this random element would be linear. This is a singly linked list, so each element has a pointer to the next element. Here's a LeetCode problem where we are trying to reverse a linked list. To implement this solution, one way is to start off by creating a new list, which starts off as a dummy node. we need to initialize the list with the dummy node because we need to reassign the head of this list to the next element of the head to a new node. And if it's null, then we run into an error. Moving on, in each iteration or recursive step of this algorithm, we are removing the head of the original list and assigning it to the head of the new list. This is repeated until we hit the base case where the original list is empty.
And our next data structure is a stack. And the best way to think of a stack is how you think of a stack of plates in real life. So if you want to add a new plate to the top of the stack, that's what you do. You put it at the very top, and if you want a new one, if you want to take one out, you pull it out from the top. And that means we have a structure where the last item in is the first item out. And this can be useful in a lot of cases. For example, in the problem that Laura just mentioned right now, we wanted to reverse a linked list, right? If we wanted to reverse a linked list, it's actually very easy using a stack, because if you put all of the items in, when they come out of the stack, they will be in the reverse order. For example, I put in item 1, item 2, item 3, and item 4. Then, when I pull them back out, item 4 will be the first in the list, item 3 will be the second, item 2 will be the third, and item 1 will be the fourth. Because of this, they're very useful data structures for reversing sequences and also remembering the last used item. Actually, a very important example of a stack is the undo button on your computer. Whenever you press Control-Z, you're essentially pulling from a stack that contains all of the commands that you've done on your computer. And whenever you press that Control-Z button, you are popping the last item. You're popping the last function that was used on your computer. So all of these functions are also done in constant time, O of 1, which is the lowest possible time that you can get when you are working with a certain function. So very snappy, very useful, but definitely not oriented towards search problems. We're going to cover an example of a problem that uses a stack now. This is actually one of the most popular coding interview problems of all time, actually. Valid parentheses. You definitely would want to run over this if you're going into a coding interview, just because of how often it shows up. You're given a string S containing just parentheses characters, as you see over here, one of the 3 types, and you have to determine if the input string is valid, if it is valid parentheses. And you determine this with 2 conditions. Is the opening bracket closed by the same type of closing bracket? And is the opening bracket closed in the right order? For example, here we see a valid parentheses string where the opening bracket is a regular parentheses, then we see a regular closing parentheses. We see a regular opening curly brace, and then a regular closing curly brace. So because of this, a stack is useful because we want to remember what the last opened one was, so to see if it matches with the newest closing string. So essentially, how we solve this problem using a stack is we're storing the reverse order. So we see a opening parentheses, we add this into our stack. We see a closing parentheses, and we pop the last item inside of our stack and compare it with it. We move on and do this with the curly brace. That's why this is a valid string. Now, this is an example of where it fails. We see an opening parentheses, we add it. We see an opening curly brace, we also add this. But when we see the next closing brace, we see that it doesn't match with the popped item from our stack, which would be this. And then we can see that this would work because they are opened and closed in the same order. It's a mirrored structure. So therefore, stacks are the best solution in cases where you want to match reverse patterns. And then another data structure that follows, that is essentially built off of a linked list, is a queue. A queue is not too dissimilar from like a line in real life, where the first person in the line, the first person at the beginning of the line, is the first one out. first in, first out, first come, first served. So there are three essential functions that you can run on a queue. There is pushing to the back, which is called enqueuing. This is getting into the line. There's polling from the front. This is leaving the front of the line to get processed. This is called dequeuing. And there, just like we saw in the stack, there's a peek operation where you can look at what's at the top without removing it. And all of these are done in O of 1 time. Our next data structure is a binary tree.
Now in a binary tree, we can store sorted and unsorted elements. The time complexity to search for a random element would be log n, and the time complexity to delete a random element is also log n. So this is a very efficient data structure. Moving on to the different types of binary trees. In a full tree, every node has 0 or 2 children. In a perfect tree, every node has 2 children unless it's in the last row. So it's completely filled. On the other hand, to be a balanced tree, the left-hand side needs to be within one depth level of the right-hand side. So if we had a tree where the left side had a depth of 3 and the right side had a depth of 1, that tree would not be balanced. A complete tree is almost perfect. However, the remaining elements are leaning towards the left-hand side. And lastly, a degenerate tree is just a string of elements to the left or right. Now let's do some binary trivia. Sorry about that. Now, which of the following are balanced? If you could put your responses in the chat box, that would be great. Okay.
So someone says BD.
It says BD.
BD.
There are a few more.
A few more actually for balance. So just to say again, a balanced tree is where, actually, yeah, that's right. It's all of them. It's where the largest difference in levels is at most 1. So we see that all of these trees actually end at the same level, or they're only one apart in their leaf level.
Mm-hmm.
Next
exactly. Question. And which are complete? Well, moving on. Oh, okay. I see some responses. So someone says BCD.
Someone said AD.
Okay.
The right answer is actually ACD.
Yep.
So
right.
Yeah.
Oh, sorry.
Yeah, so essentially what constitutes a complete binary tree is a binary tree where all of the levels are either filled out or the last level has all items moved to the leftmost side. So in this example B, it wouldn't qualify because we see that this node could be over here if we wanted it to be complete, but it's not. In all of these cases, the leaf nodes are all pushed to the very left, or it's completely filled out. So these are examples of complete trees.
Oh, there's a question in the chat. What if the bottom level was rightmost?
There's not really a justification for why it's leftmost or rightmost. It's just the definition that people give for a complete tree is one where all of the yeah, it really just is like that.
You like that?
Yeah, I mean, binary trees aren't always sorted. There's binary search trees which are sorted, in which case like getting complete structure is not really, a priority so much as sorting. But in a case of just a regular binary tree, if you wanted to get complete, you'd probably want to try to put things into the leftmost side of the tree.
Okay, so now which of the following are full? I see. That's right. Okay, so A is a full tree because all of its nodes have 0 or 2 children, and so is D because that's a perfect tree. And then now which are perfect?
Great. Yeah, D is actually a perfect tree because it is completely filled out to the the bottom row is completely filled out. All of the leaf nodes terminate at the exact same place, and this entire level is full. And degenerate, we actually don't have any. So moving on to binary heaps.
Yep, so, sorry. Another data structure here. This one is really similar, but here are some of the operation and time complexities associated with this data structure. So to get the root that's constant time, to remove the root, that is log n, and insertion and deletion will still be log n. Now there are two types of binary heaps. One of them is the min heap, where the root element is the minimum, and the other is the max heap, where the root element is the maximum. So binary heaps are particularly useful to implement priority queues. And overall, a priority queue structure makes it a lot easier to insert and reorder elements based on their priority. And it just allows us to deal with the prioritized cases first.
And then our next data structure is a hash map. And a hash map's main functionality is storing key value pairings. So this is really important because when we looked at all of our other data structures that were search oriented, like for example, your binary tree or your arrays or matrices, we always saw O of n search time or O log n search time, which are not like very bad, but they're also not the best that we can do. The best that we can do in terms of search complexity is O of 1, constant time. And hash maps provide us amortized O of 1 time, meaning usually they're done in O of 1, constant time. How a hash map works is you have a key value pairing that you input, and the key is passed through a hash function. Your key can be something like, for example, your driver's license number, or your PID at school. And the value associated with it could be any data that is related to that key. In this example, we're using letters and how many times they show up in a given text. So for example, if we see L show up 3 times, we want to store that data as a as a count pairing right here. And how the hash function works is it takes that key and it mathematically converts it into one of the indices inside of this array. And each bucket, each cell inside of this array is used to store a linked list that contains all of the keys that have been hashed to that specific index. For example, A was hashed and it came out to a 1 and it was stored here. C was hashed and it came out to a 2 and it was stored here. Now, you might see that there are 2 in the same cell, and why we have this is because sometimes you can have hash functions that assign the same, or it can assign different keys to the same index inside of the hash table. And the reason this happens is because hash functions can often, not be as sparse as you want them to be. And we would usually be having a table that is a lot larger and a hash function that is, optimized to make sure these collisions don't happen. But that is why we say amortized when we talk about the time complexity, because there is a possible worst case in which all of your elements get sorted into the same index bucket. And this drives your search time all the way up to O of n, because you have to search through this entire linked list to find that one specific item you're looking for. And the operations on this are O of 1, but with that little asterisk over here because it is amortized. And one possible question which you could solve with a hash map is k most frequent elements. This is, whenever you see frequency used in a coding problem, in a coding interview, immediately jump to hash maps because they are the best for aggregating counts inside of like a data structure. You want, and also in Python, these are called dictionaries if like you're not familiar with using Java. So the k most frequent element solution is this. You are given an array of integers, right? And you want to give the k most frequent elements. In this case, k is equal to 2. So we want to get the 2 most frequent elements out of this array. So we would iterate through this array right here. And each time we see a number, we would put in that number into our hash map with the amount of times we've seen it. If we've seen it already, all we need to do is add 1 to the existing count inside of the hash map. And doing that, we go through this entire array, and we have aggregated a hash map where we have the pairings of 3 to 4, because we've seen it 4 times, 2 to 2, because we've seen 2 times, and 5 to 1, because we've seen 5 once. And ultimately, how do we get the k most frequent? We use the priority queue that Laura had talked about. So we put all of these key value pairings into a priority queue and rank them based on the count number. And once we pull from this k times, we have gained the k most frequent elements inside of an array. And it's a really simple solution because we are breaking down this more complex problem into 2 separate problems of finding the largest and of aggregating.
Okay, so over here we have a bunch of nodes, and one type of graph is a directed graph. So as we can see, the edges are directed from one node to another. And in a undirected graph, the edges will be unordered pairs, so they don't have a set direction. Moving on to graph properties. In a directed graph, if there is, okay. So in a directed graph, we see a node pointing from A to B. So in this case, A would be the predecessor and B would be the successor. So there's that. And for both types of graphs, the edges can have weights. So this is useful for when you're like measuring the distance between cities and stuff like that. And in the table below, we see the degrees. So in a directed graph, A has an in degree of 0 because there are no arrows pointing towards it, and B has an in degree of 1 because there's only one arrow pointing towards it. Likewise, A has an out degree of 1 because it has one arrow pointing outwards, and B has a out degree of 0 because, wait, did I say? Well, A has an out degree of 1 and B has an out degree of 0. In degree and out degree don't really apply to undirected graphs because there is no direction associated with that edge, and overall, they all have a total degree of 1. So we'll be discussing 2 main types of graph searches. One of them is DFS and the other is BFS. In DFS, our main goal is to be as far reaching as possible in the graph. So we're just trying to get from one end to another, and this makes it useful to implement finding the shortest paths from one city to another and stuff like that. On the other hand, in BFS, we are reaching for our neighbors first and branching out from there. So if we wanted to search through someone else's friends before moving on to someone else, that's what we would use. And for the time complexity of both BFS and DFS is big O of V plus E, where V is the number of vertices and E is the number of edges. This depends on the data structure that we're using, if it's an adjacency list or matrix. And if it's an adjacency matrix, the time complexity is V squared. And if we use an adjacency list, it'll be V plus E. So some applications. One way to use a graph is to map the world cities that we can see here, where each edge has a property that can hold the distance between two vertices. And another application is social networks. So in Facebook, someone with a lot of friends may have a bunch of edges branching out, while someone with less friends and connections wouldn't have as big of a graph.
And here's an example of a LeetCode problem using graphs is a number of islands. So basically how this problem works is we have an m by n grid, a matrix of ones and zeros. Here I've represented zeros graphically as blue and ones graphically as, these yellowish colors. So our goal is to return the number of islands. An island is formally defined as any group of yellow squares that is linked by a horizontal or vertical connection to another yellow square. So here we see we have 3 yellow squares because these are all horizontally and vertically connected. Same goes for this grouping and this grouping. And now, even though we see that these squares are close together, they are diagonally connected, which is not covered by our definition of an island. So there are 4 islands in here. Now, how we would use a graph to solve this problem is we would use BFS because we want to traverse all of these connections, and anything that involves the connection of different components can be visualized or can be approached as a graph problem. And this is essentially a graph problem because every single time that we want to classify something as an island, we have to see how far it goes out. For example, we would iterate through each of these matrices element by element, and each time we see land, we would start a breadth first search. We would go to the neighbor of the first item. We would see if it has any undiscovered neighbors. For example, like seeing a 1 here, that would be a discovered neighbor. So we would change that to 0. So it's now water and thereby discovered. Then we would check the other neighbors of this node. For example, we check here and here, we'd see that there are water, but we see that this is land. So then we move over to this one and we check, we turn this into a 0 because we've traversed over it and it becomes water. Then we go here and we check to see if it has any neighbors. We repeat the same process where we move over to this node, change this to 0. We check neighbors here, and that terminates the search because there are no undiscovered neighbors. There's only water and discovered neighbors. And that is all encapsulated into one call to BFS, which means that once we're done doing that one search, we increment our counter by 1 for however many times we call BFS. And the same process occurs here. We see this node, we move to the right, we see that this node has 1 undiscovered neighbor, we check it, we move to the left, and then we turn all of these blue, and that's all encapsulated inside of one BFS function call. The same process applies for these later problems. And with that done, we have counted the number of islands because it is the number of times we have called BFS. And if you guys have any questions, feel free to leave them in the chat. We actually got a question about the previous hash map problem. How come we couldn't iterate through the array and use a count variable to keep how many times it is seen? And the one with the highest count variable is the most frequent. That's because when we're iterating through that array, we have to keep those counts for all of the elements inside of the array. And you don't necessarily know when you're iterating through that array what all of the unique values inside of there are. Like, for example, there could be 1,000 and we would want to get like the 2 highest, right? So you wouldn't just want to store like the most frequent one. You'd want to store the most frequent one, the second most frequent one, and the third most frequent one because of the case where the person asks for the 3 most frequent. So it becomes harder to do that kind of thing when you're working with a array and just like iteratively looking through it, because in that case, you have to iterate over it once to collect the count for each item inside of it. And then it becomes a problem of, quadratic complexity because you're iterating once for every element inside of the array. That's n squared time. But when we do it with the hash map, it's O of 1 time for actually like aggregating, and O of n time for just iterating over the array altogether. And then it's O of 1, and then it's O of n, or O of k time, actually, in the case of getting the k most frequent elements. So the overall complexity comes out to O of n, as opposed to O of n squared. And with that said, how to use LeetCode to prepare for your interviews. So whatever you have inside of your, your LeetCode knowledge, like no matter how many problems you solve, it's also important to be able to present that knowledge that you have to your interviewer. So like to be able to communicate the thoughts that you have clearly. Whenever you're going into an interview, you shouldn't dive directly into the problem. You should speak to your interviewer about all of the possible solutions that you see. And you should also like pick out keywords in the prompts that they gave you. For example, like frequency, you should tell them that you immediately think about a hash map when you see the word frequency. Or when you see that you need to reverse a sequence, you should say that that immediately makes you think of a stack. And by being transparent about your thought processes through this entire situation, you're able to make sure that your interviewer knows that you are cognizant of time complexity, storage complexity, and all of this, what you're like, what you're thinking. And I think we have a comment in the chat. Yeah, exactly. So they don't necessarily like necessitate you to say it, but if you're like really struggling with like saying it out loud, they will like prompt you to say it. So you should try, like, whenever you do coding problems on LeetCode, also try to speak to yourself and speak to your imaginary interviewer as if they were there, and try to say out loud like why you're choosing a certain solution to a problem or why you want to approach it in a certain way. So before you go straight to like typing, definitely think about your design for the solution a lot. And the next part is also being able to solve problems you haven't seen before. This also goes along with like, trying to look for the most efficient solution. Sometimes there are intuitive solutions that seem like a lot easier, but actually have high time complexity costs. So trying to morph it into a problem that uses one of these data structures where you can quantify how complex the problem really is really important. And the next issue is breaking the problem into simpler concepts or like components. And we saw this in the case of the k most frequent elements, where we broke down the aggregation logic into the hash map. And we broke down the logic for picking the largest elements into the priority queue, like the max heap. And this can be broadly applied to a lot of different coding problems. Usually the problems that you'll face, not only in your LeetCode problems and your coding interviews, but also in your job, will be multifaceted. You don't necessarily have to solve your entire issue with one tool. They want to see you be able to use multiple tools in the most efficient ways. And always think about efficiency, speed, think about your big O notation, how much time it takes to run through that entire process. Even if you're not very familiar with big O notation, you can usually tell based on like what data structure you're using, how much time it takes to do a certain process. And that's also something you should be cognizant of in your LeetCode and your coding interviews. Does anyone have any questions? Feel free to unmute or even leave it in the chat. Oh, thank you. All right.
Okay.
And
I think if no one else has any other questions, there's a survey on the next slide.
Oh, actually, I think let me add that in real quick. I'll post that in the chat. There's a survey that we want to give you guys. I'm gonna stop sharing real quick. Do you recommend just hopping into LeetCode, or do you recommend implementing these data structures on your own first and then going through LeetCode? So actually, that's a pretty important question. You know, when you're dealing with a coding interview, there is usually like two sections. There's a section where they ask you how to, you know, like they give you a certain situation and they ask you what data structure you would use for that certain problem. For example, for one of my coding interviews, I was asked what data structure is best for holding like a library registration database, like connecting users to the books they've borrowed. And I explained that it was a hash map, and they asked me more questions about how hash maps work, like the hash function, how you deal with like collisions and stuff like that. So they're both like pretty important in and of themselves. So if you implement those data structures on your own first, it gives you that ability to understand at a base level what's actually happening when you're doing all of these commands. And that also makes your you know, explanations clearer when you're doing sort of problems that like actual coding problems, and you have to explain the time complexity of everything because you've built it from the ground up, right? And going through LeetCode is also equally important because I think LeetCode questions have a very different paradigm than you would have when you're working with you know, programming assignments, because I think our programming assignments in our curriculum are mostly geared around implementing the data structures from the base up, and they're not really oriented towards like all of the different uses for those data structures. So yeah, I would say both are equally important, but you would probably want to start with, if not implementing the data structures, at least studying how they work at a lower level.
Yeah. I think just to like narrow down the data structures that you want to use, looking back on classes like DSC30 and like DSC20 and looking at those big data structures that we really like took a deep dive into would be really useful before starting to do LeetCode regularly. Other than that.
Also, if you're more of a reading person, the Cracking the Coding Interview book is an amazing resource for preparing for coding interviews. They release new editions like all the time, and it has a lot more than we can say in like a 1 hour, you know, workshop, and it really goes into depth about all of these different concepts.
Yeah.
Cracking the Coding Interview.
Let's see. Okay.
Trying to find, trying to get that form real quick.
Oh, is it a new link?
Oh yeah, but there is a link to these. There's a link to these slides over here. If you guys want to take a look at these and keep these on hand. Oh, thank you. Yeah. We used SlidesGo for the templates. They have really good presentation templates. One sec, I think.
Oh, I got it.
Oh, you got it?
Yeah. Let's see. Well, I guess if there's no other questions, thank you for coming to this workshop.
Right. And I will post that survey in just a second. So sorry, if you guys can hold on for just a minute. I'll get that out to you. All right. All right, got it. Let me send it out to the chat. Okay, that should be, one moment. All right, Laura, I sent it to you. Do you know if you could drop it in the chat?
Okay, I just pasted it.
Oh, I don't see it in the chat. Probably stop the recording here.